Hello.
Okay, we have a speaker, Georgii Riabov. So, if you are ready, Georgii, are you ready?
Yes, we can start, yes.
Okay, we can start.
Okay, so I started the demonstration. This talk will be devoted to the problem of constructing coalescing stochastic flows on some complicated spaces like metric graphs. So I will start with the definition of a stochastic flow. So we will consider the locally compact separable metric space, and the stochastic flow on the space E is a family of measurable random mappings of E such that we have the weak flow property, independent increments, and stationary increments. So independent increments means that on non-intersecting intervals, mappings act independently, and stationary increments means that the distribution of the increment depends only the length of the interval. So here I wrote the flow property in a weak form because one of the main questions I will address today is actually how to get the strong flow property. We will say that we have a strong flow property if for all RST, X, and omega, we have the evolutionary property. So it holds without exceptions. So as a motivation, I will briefly recall some well-known results that regarding smooth stochastic flows. So if we consider the stochastic differential equation with Lipschitz coefficients, then it is known from works of Kunita that there exists a family of random homeomorphisms of the real line that consists of solutions to the stochastic differential equation. And also psi can be made a strong flow, and moreover psi can be realized in the following way. So on the bottom of the slide we see that we have the strong flow property, but also we have the stronger form of stationarity. So here psi st omega x is equal to psi 0 t minus s, where omega was shifted by some mapping theta s. Here omega can be taken as a classical Wiener space, so it is a space of all continuous functions. The probability measure is the distribution of the Wiener process, and theta is a shift. So the last result is a theorem of Arnold and Scheutzl, and this result means that in the terminology of Arnold, it means that the flow psi is generated by a random dynamical system. So I will give the definition. The random dynamical system consists of first a metric dynamical system. It is a probability space equipped with a measurable group of measure-preserving transformations. And the random dynamical system is a measurable mapping that satisfies the perfect cocycle property. So here in the perfect cocycle property, we see that phi at the time t plus s acts as phi at time t, but the probability argument was shifted by s. So this shift is comes from the group of measure preserving transformations. If we have the random dynamical system, then we can define the strong flow. So psi st is defined as as the action of phi on time t minus s and corresponding to theta s of omega. In this form, actually, the strong flow of psi is equivalent to the perfect cocycle property of phi. So moreover, when we have a random dynamical system, so we automatically have a measurability of the flow in all arguments, because a random dynamical system is assumed to be a measurable mapping. Of course, for smooth flows, for like on the previous slide, we can get much more than just measurability. We can get continuous or even continuously differentiable random dynamical systems. But so in my talk, I will consider discontinuous flows. That's why in this definition, I only impose measurability of the mappings. Okay, similar results.
Georgii, let me interrupt you with such question. What is the advantages of the strong flow property over the usual flow property, like you formulated in the first slide?
Here,
why we are looking for this justification of such strong flow property?
Here maybe it is more important that we get a measurable mapping, which is measurable in all arguments. When we have the flow which is measurable in st omega x, then we can apply various types of ergodic theorems and so on.
Mm-hmm, mm-hmm.
And
maybe in this way we can relate the property of this metric dynamical system on the initial probability space and the properties of the stochastic flow.
Yes, yes.
Mm-hmm. Okay.
Yes. And we will see today that actually in the case of coalescing flows, the choice of probability space becomes an interesting question. Mm-hmm. So now I will go to this part. So similar results, but weaker results. They're true for general stochastic flows. I will need the construction of general stochastic flows, so let us introduce finite point motions. When we have a stochastic flow on some space E, we define the function p xb. So this is a probability that that points x1, xn under the action of the flow, they belong to set B at time t, and this is a transition probability on the e to the power n. So with every stochastic flow, we get a sequence of transition probabilities that correspond to finite point motions in the flow. And this sequence satisfies several natural consistency properties. So this is very much like finite dimensional distributions of the stochastic process. We have, I will denote these properties by 1 and 2. So the first property is it says that we have a projective family of transition probabilities. And the second property says that, well, if we start from the same point, then the action of the flow is the same at this point. And additionally, I will assume that all transition probabilities are Feller. Then there is a fundamental result, a theorem of Darling. It says that there exists a strong flow such that its finite point motions are given by transition probabilities Pn. So here I put quotes because so the flow constructed in this theorem, so it is a strong flow in the sense that we have evolutionary property without exceptions, but it is not, it doesn't satisfy the definition because mappings from this flow are not measurable. And in the bottom of the slide, there is some kind of explanation because these flows were constructed in the very general case. As a probability space, it was taken actually the space of all strong flows equipped with a cylindrical sigma field. So on such a large space, of course, it is hard to construct a measurable element. So though there is a measure preserving group of transformations, but it is also not measurable. The measurable modifications were constructed later by Lejean Raymond. They proved that there is a weak stochastic flow. So now mappings psi are measurable, but the flow is weak. And also the probability space was the space of all measurable mappings equipped with the cylindrical sigma field. So again, there was a group of measure preserving transformation, and it was also not measurable. Okay, so these are two basic existence results. Now I will also recall one my result that regarded constructing of coalescing stochastic flows on the real line. Some time ago, I proved the following theorem. So if we additionally assume three more properties of transition probabilities. So the first is the analog of continuity of trajectories. The second is an estimate on the meeting time. And the third is absence of atoms. Then it turned out that one can construct a strong stochastic flow. Moreover, this flow is generated by some random dynamical system. So we get a strong flow of measurable mappings. And these conditions, they were rather general. So we applied them to Aratia flows, to Harris flows. But it was crucial that we worked on the real line. Today I will try to go away from this assumption. Another remark is that while proving this theorem, we found that a special care must be taken to the points, to so-called fresh points. But I will speak in more details about this in a while. So here, a natural question is whether we can extend this result to some other metric spaces that are locally like real line. Okay, and I will do this today for metric graphs. So let us formulate some assumptions on the metric space. So what we will call a metric graph. We will assume that the space is path connected So there exists at most countable set of vertices V, such that when we remove vertices, we get some partition of the space into open subsets, such that each set EI, so EI is an edge of the graph. Each edge EI is isometric to an interval, probably unbounded interval on one side. Okay, by E small, I will denote the isometry. Okay, and for each vertex V, by this I of V, I will denote the set of adjacent edges. And we also assume that to each vertex we have finitely many adjacent edges. So K of V is the number of these edges. The last condition, the absence of loops, it's not important, but convenient. Okay, so these are our assumptions on the metric space. Let us also fix some dense countable set.
Let me ask you, the last condition means that we have no like simple loop, yes, which are constructed from the one interval.
Yes, so each edge has different ends.
But it is allowed that we can have some circles, yes, in the graph.
You mean they can be constructed from different edges?
Yes, yes.
Yes, we can, and
yes, it is possible. Okay.
Yes, it is possible. So S will denote a dense countable set. So here are two examples. So yeah, we can have some circles. Graphs like in example one, they're called star graphs. These are graphs with the one vertex. And also here, so in like from the very beginning, from the when we introduce the set of adjacent edges, I enumerate them. So around each vertex, I fix some enumeration of adjacent edges. Okay. So my aims today will be to define a space of coalescing stochastic flows on the metric graph, and to show that this space has a good measurable structure, and to formulate some conditions on transition probabilities under which we can construct a stochastic flow by a random dynamical system. So now I will give the definition of the space of coalescing flows on a metric graph. By Cx, I will denote the space of all continuous functions that are defined from S to infinity and take values in E, and they start from the point X. So the product, this product, then it is just the space of all possible functions that start from all points of E at all times. Okay, and omega will be a subset of this space. So conditions are the following. First of all, we have evolutionary property. This is F1. F2 means that at any time S, trajectories that came from some previous time form a dense set in E. Then the third property is that every compact in a finite time maps into a finite number of trajectories. Condition number 4 means that every trajectory immediately coalesces with some other trajectory that came like from so-called from a new point. And the last condition is regularity. So if x is a new point at time s, then we distinguish two cases. So if x lies on an edge ei, then we impose continuity from above. So here we see that y converges to x such that ei is a isometry with the interval, so ei fixes already some ordering on the edge. So y converges to x from above. And if x is a vertex, then we choose the first adjacent edge, and we impose continuity along this edge.
Georgi, let me ask you about the condition F3. Do you suppose before that E is a connected metric space?
Yes.
Okay, because if not, then it can be possible that maybe.
Yeah, we formulated in that it is path connected.
Okay.
Okay, so this is our space of flows. So we equipped it with a cylindrical sigma field. It means that for every fixed s, t, and x, the mapping evaluation mapping is measurable. So the first main result is that on this space, if we consider evaluation mapping as a function of all variables s, t, x, and omega, then it becomes jointly measurable. So I will show the proof now, but before that, what corollaries we have from this lemma, that we can define the shift on this space, and this shift becomes so it becomes a measurable group of transformations. And if we define just the evaluation mapping, it becomes a perfect cocycle over the shift theta. Okay, so now let's turn to the proof of the theorem, of the lemma, sorry. The lemma states that if we consider some open set U, then the set STX omega such that omega STX belongs to U is measurable, is jointly measurable. So here, the most complicated part is to take starting points outside of omega. Because in T we have a continuous function, so we know that such mappings TF that maps to f of t, it is jointly measurable when f is continuous function. So we will try to remove s and x from initial conditions. To do this, we will distinguish two cases. So when x belongs to Rs omega, and when x doesn't belong to Rs omega. So I recall that Rs omega is the points that that arrived like from the past at time s. So the first task is to write this condition. I will show that this condition actually it is a measurable condition in all arguments. So here the main equivalence that this condition is equivalent to existence of Rz, where R is rational, Z is from the set of separability such that R is less than S, and omega Rs of Z is equal to X. It means that if the point X is the value of some if it belongs to some trajectory that came from the past, then we can take this trajectory started at rational time and from a point of dense set. So here sufficiency is obvious, so we prove necessity. So if X belongs to Rs omega, then there exists some u less than s and some y in E such that omega u sy is equal to x. Let us recall the condition F4. The condition F4 means that every trajectory immediately coalesces with the trajectory that started from a new point. So we can assume that y is a new point. But if y is a new point, then we have some continuity at y. This is from one side, so we have some continuity at y. Also, we have the property that every compact immediately coalesces into finite number of trajectories, together with continuity. So it means that we can like move a little bit y, and the value of x will not change. Okay, so in fact we can assume that y belongs to some edge. And now if y belongs to some edge, it arrives us to x, and we have some continuity at y. So there is another trajectory that have coalesced to y before leaving the edge, and then in this small area we can find the needed point Rz. So this is how all these properties work to find a trajectory that started from rational point and from the dense set. Okay, so using this condition, we can write the set of we're interested in as follows. So let us take the union in all Rz, STX R omega, no, not R, STX omega, such that R less than Z, omega RSZ is equal to X. Okay, but now I can replace omega STX, I can replace it by omega RTZ. Okay, because here, because of the evolutionary property. So omega RTZ is equal to omega ST of omega RSZ, but omega RSZ is equal to X. So in this case, we achieved what we wanted. Yes. So the if x belongs to a trajectory that came from the past, then we can remove s and x from initial conditions. And if x does not be, if x is a new point, then either we have either x is an either x belongs either x is a vertex, so x is a new point, and when x is a vertex, I can write omega stx as a limit sty, and y converges to x, y belongs to some edge 1x. Well, and it is, I think it is understood that, so now we have y is, here y can be taken from the dense set, so it is okay. We removed x from initial conditions, but also we can remove s from initial conditions, again, by the property that trajectories that came from the past, they form a dense set. Okay, so if this is x, this is y, then we can choose some trajectories between x and y that came from the past and actually apply the previous considerations. Okay, and when the last case which we have to consider is when x is a new point and x belongs to some edge. But there we also have a fixed type of continuity. So basically it is the same as the case when x is a vertex. So this representation shows that on our space, evaluation mapping is measurable with respect to all arguments.
Can I ask a question?
Yes.
I do not quite understand the reasoning here. When you say that you have points somewhere in some area, then this point, starting from this point, we have to coalesce with any of those two trajectories, right? Is this correct, that you assume this?
Yes. We can do this because y belongs to some edge, and it means that y will still be in edge for some time. Yes, so y will not leave the edge for some time.
Yes, so you have to make sure it does not go to some vertex during this time. So
yes,
and then it is
yes.
okay. Okay.
Okay.
May also I ask a question?
Yes.
So when you formulated your result, really I was expected that probably you will construct the just the measurable stochastic flow, but as I understand you correctly, your idea was to first of all define very nice space omega, and then just construct the stochastic flow, say in like Darling did that, I mean without caring of measurability, and measurability you will get as a property which comes from the structure of the space where you define the flow. Do I understand your idea correctly?
Yes, so the flow will be a canonical flow in this space, yes.
Could it be exactly that approach? No. Could be exactly the problem in this approach that that you cannot extend that result for two-dimensional case or three-dimensional case, that exactly that you want to build a very nice space where you defined the flow. Probably if you would just try to construct the flow which is measurable, but without defining it on very good space like you did here, maybe that result could be extended for larger dimensions.
maybe.
But you don't have any ideas where could be a problem exactly with that
No,
one.
so the problem of constructing general stochastic flows, it is a complicated problem. And as we saw, I think as we saw from examples that the choice of the space, usually it is the reason why we don't get very good properties in general, for general flows. Of course, if you assume some continuity and so on, then you will get good modifications.
Vitaly, you see the picture in the page with this Y, where Alexei Rudenko asked about this picture, and you see that Georgii still have a possibility to keep the one-dimensional arguments. He still can use the order.
Yes, yes.
Yeah, this is important. And in two-dimensional space, we lose this possibility.
Yes.
Also, Georgi, I have a question. This is a nice construction, but what about such question? How rich this is the space of such formal flows relatively to arbitrary graph? Because a graph with count of number of vertices can have a complicated structure. So do you expect a rich space of such flows?
I considered some examples only for star graphs.
Mm-hmm.
When we consider star graphs, I think we can construct some examples. In general, it is a work in progress.
I see, because I'm just thinking about such graph with a count of number of vertices, like maybe you remember this very well-known picture of Heisenberg group, of metric on Heisenberg group, where you have such like rectangular structure which comes to infinity, yeah, and where we have all rectangles. So have to be careful about the examples of the flows on the arbitrary counter graph.
Yes, yes.
Mm-hmm.
Yes,
Okay.
but it is still a question for me.
Mm-hmm. Yeah, yeah. Okay, let's go.
Okay, let's continue. Okay, so we have discussed this measurable structure of the space, and now we need to construct the probability measure on the space of omega f. So I impose the usual three conditions that are consistency and failure property, and additionally, so these three conditions, they are very similar to what we had in the one-dimensional case. So we also have condition number 4 is a condition for continuity of trajectories. Condition number 5 is the estimate on the meeting time. And the condition number 6 is the absence of atoms. So condition number 5, on each edge we have an estimate on the meeting time. Okay, then under these conditions we can construct a random element in the space of flows. So psi will be a stochastic flow. So I will define it on some other probability space, but then take probability measure as the distribution of psi. And we will construct it with such properties that this formula reflects. So this formula means that when we start even from some random points measurable before time s and apply the flow, we get the needed finite point motions. So actually, this formula, it combines independent increments with stationary increments and with a distribution of finite point motions. So now we will discuss this theorem, but as a corollary, if we take probability measure as the distribution of psi, then we get actually a metric dynamical system, and phi is a random dynamical system, and it defines, and the canonical flow, now it will be a stochastic flow, and it will be a strong flow and measurable. So now the theorem is proved in more or less in a standard way. So first of all, we define the skeleton flow. It means that we define a countable system of trajectories that start from all points of the dense set at all rational times. And we check some properties that are satisfied by this countable system of trajectories. So the first property is that actually all these rational points are new points. Yes, so we never come back to a point of type PU. And then, the first property is just the consequence of absence of atoms. Second property is the consequence of coalescence. The third
Georgii,
property.
why do we have SP1? Could you please explain one more time?
Because 1 point motions, they have no atoms.
Okay, thank you.
It was condition number 6.
Thanks.
Then, condition number 3 is that the range of this system forms a dense set at any moment of time, and the last condition means that trajectories that at time s they belong to a compact set, at time t will coalesce in a finite number of trajectories. Okay, so let's discuss the proof of the lemma. It actually repeats what we did for the flows on the real line. I will briefly recall how we proved this. So first of all, let us discuss property number 3. We have this condition on transition on 1 point motions. Now let us work on a single edge. This condition can be extended to the following. So if we take the probability that during the time from 0 to t, our process that started from x and its maximal deviation was greater than epsilon, then so this probability is also of smaller order than t when t goes to 0. And this is also a consequence of ordering of the real line, because if we consider the probability that so we can estimate this probability as follows. So either we have
Georgii, is this well-known fact for one-dimensional diffusions? or we have to work with edges. This is a problem. Or
No, this is completely one-dimensional fact. Well, yes, I think maybe this is well known. Just the idea is that at time t, we either deviate by epsilon over 2, or not, but then we have some kind of this behavior. Yes, so in any case we will have a deviation of order epsilon over 2, and this is when divided by t, this converges to 0. Now when we have this property, again on the edge we can do the following. Let this be our edge, and we can consider such box and divide it into small vertical strips. So this is the edge and this is the time, and we consider the event that all trajectories that started from this partition did not leave the so they didn't deviate too much from initial point. Okay, so let us.
Georgii, I have one more question. I forget. Do you assume that one-dimensional process is a failure process?
Yes.
Okay, thank you.
Yes. So
failure in which sense?
I'm sorry.
In which sense failure? There are many definitions, different definitions.
So the transition semigroup defines the failure semigroup of operators on the space of continuous functions.
So bounded continuous functions or vanishing at infinity or
Yes, bounded.
okay.
Yes.
Also, okay.
Okay, so here we do the following. Let us consider some partition of the timeline and consider the event an such that for all k, the maximal deviation from psi k to psi k plus 1 of our flow y psi k t of x minus x. Let's consider a complementary event. There exists k such that this is bigger than delta. Since we will make a partition very small, such that the probability of for a single maximum will be less than the length divided by some 2 to the power n. Okay, if this would be like b minus a divided by their number kn. We can do this by this property. And if the probability for a single maximum is of this type, then the probability of an is estimated by some constant divided by 2 to the power n. So it is a convergent series, and we can make the following conclusion. So if we fix such a box around the edge, around the point on the edge, then for large enough n, all trajectories will not, all trajectories on small intervals of time, they will not deviate too much from this box. So they will intersect the neighborhood of the point x. So this proves that trajectories that came from the past, they form a dense set.
Mhm.
And so this is what regards property number 3. And property number 4, if we take n points around, let's say around some vertex, then we have the estimates on the meeting time. And if we denote by dn the number of these points at time t, the number of points that remained at time t, then this can be estimated by k of v plus the sum j from 1 to k of v. And here will be some m ij t aj minus m ij t of 0. Well, here I mean that we take some finite lengths on each edge. V is a vertex. So this is a well-known estimate. It is just repeated for each edge around V. Okay, then let us construct the flow from this skeleton flow. Well, the definition, it exactly reflects the regularity that we need for the flow. So if a point x already belongs to some trajectory, then we don't change it. If x is a new point that belongs to an edge, we approximate it from above. And the limit exists because actually the limit becomes 1 point. Similarly, if x is a vertex, then we approximate it along the fixed edge. Okay, as a consequence, we get the flow psi. And from this construction, we see that when s is less than t, then actually the value of the flow will always belong to the value of the skeleton flow. So every trajectory immediately coalesces with the trajectory that came from a new point. What remains is to verify that we get a correct distribution of finite point motions. And this can be done by the following approximation scheme. So we take for every point of the graph. So when it is a point, when it is a vertex, then we approximate it by trajectories from the skeleton flow. So Lm of x, it is the number of the first trajectory that belong to the first adjacent edge, and that is 1 over m close to x. If x belongs to the edge, then we approximate it from above. Again, as a consequence of immediate coalescence, we have that both the values at time s, they converge to x, and the values at time t, they converge to the value of psi at time t. And from this, we can deduce that finite point motions of the flow psi will be given by transition probabilities Pn. So actually, this construction is quite straightforward generalization of construction from the real line. So what was new is to get this measurable structure on the space of metric graphs. Yeah, okay, so this is actually all that I wanted to show today. So thank you.
Thank you. Maybe some questions?
Yes.
Mm-hmm.
I still have a question about that part. I have an example. I'm not sure if it's working, but what if we have just star graph with 3 edges, okay? And we have a motion such that it goes from one edge, from one of the edges to other 2, but it chooses which one depending on which moment of time it arrives. And if it arrives on, and we can choose it to be not measurable, this moment of time, from some non-measurable set. Is it possible that there will be some non-measurability here in this type of situation? If we choose a moment of time to turn depending on some non-measurable set, where will be the contradiction to the assumptions?
Well,
This is not failure.
Yes, how the one-dimensional motion will be a good process then? One-point motion, how it will be good process?
Yeah, but I am only constructing omega right now. I'm not constructing the process.
so here we have omega must have this instantaneous coalescence property. So every compact must be mapped into finite number of trajectories.
No, Alexei, maybe you are right. We can construct very complicated example of this coalescing path set, but then when we want to discuss the probability structure on this set, we will not able to define good processes. So maybe this is exactly the question which I asked too. How rich is the set of this path with such properties without probability, before the probability? But we cannot equip it with good probability, maybe.
Yes, but okay, okay. Probably, unfortunately, I cannot think how to finish this example. But maybe I think there are some questions still about measurability and also about this graph. This graph. I don't think you don't. I think you don't want the different situations that can arise. For example, if you have a point which is vertex, and you have a sequence of vertices that converges to this vertex. Yeah, you don't want situation like this, but you never said something about.
Yes, Alexei, I thought about this also, but you see, Georgii used the distance along the graph.
We don't have. I don't think that it is possible in our graphs.
Yeah,
Okay.
he used distance along the graph. It is metric space, so it does not matter when you embed this graph into the space. Then you must have that metric in the graph is consistent with the metric in the space, but it cannot happen. Yeah.
Okay. Yes. So by definition, it's not possible. That was the question. Thank you.
A finite number of vertices or not? Not necessary.
It is at most countable.
Ah, okay.
But each vertex has finite number of edges. This is important.
Georgii, also let me ask you, suppose we define such a coalescing flow, for example, on the usual finite dimensional lattice. Yes, like we have rectangular lattice in RD. It seems that it is possible. Do you expect some new effects relatively to Aratia flow on the real line on this graph? What kind of new effects can be obtained there?
I think what interesting effect will come from the duality. because we know that on the real line, the Aratia flow, it has a dual flow, and the dual flow is also the Aratia flow. What if we consider the analog of a dual flow, but on the metric graph? It seems that it will not be a stochastic flow of mappings. It will have some kind of splitting of mass.
But you see, Aratia flow is a strong, no, it is not strong, but maybe you cannot, when you construct Aratia flow, you can really construct a skeleton flow and strong solutions to some stochastic differential equations. And with triple points, you don't.
Yes.
Yeah.
Yes, you mean that Walsh Brownian motion, yes?
Okay.
Yeah, so I'm sorry. So yeah, so we expect that the duality will be interesting for such flows.
Yes, because you still have some circles, and as for Aratia flow on the circle, yes, we have some new effects. Okay, I see. Okay. If there are no other questions, thank you very much. And then we end our session for today. See you next week with my talk. Bye.
Bye.
Thank you. Bye.
Goodbye.